This video is about summation notation, also called sigma notation, because this crazy symbol here is the capital letter S, or sigma, in Greek. Now, how do I read and interpret summation notation? This number here is the starting term number, the number below. Starting term number. And the number above the sigma is the ending term number. Notice it does not tell you the number of terms, but the ending term number. So I have terms 1 through 4. 1, 2, 3, 4. Turns out there are 4 terms in this case. Here is the rule for the sequence. So what it tells me to do is take the numbers 1, 2, 3, and 4, one at a time, plug them into the rule, and then add them, because this is called summation notation, so you add them up. So this creates a series. So when n is equal to 1, n equals 2, n equals 3, n equals 4, I'm going to have this. 2 times 1 squared plus 1 plus 2 times 2 squared plus 1 plus 2 times 3 squared plus 1 plus 2 times 4 squared plus 1, which turns out to be 3 plus 9 plus 19 plus 33, or 64. So the actual answer when I say evaluate would be 64. Let's look at the next one. N equals 0 to 3 of negative 1 to the n times 2n. So how many terms are in the sequence? Not 3. It turns out there are 4 terms still. N equals 0, n equals 1, n equals 2, n equals 3. 4 terms, not 3. So you have to be careful. That's one mistake commonly made by students. So when we evaluate this, we have negative 1 to the 0 times 2 to the 2 times 0 plus negative 1 to the first times 2 times 1 plus negative 1 squared times 2 times 2, and negative 1 to the third times 2 times 3. So negative 1 to the 0 is just 1, and so this is 1 times 0. 2 times 0 is 0. Plus negative 1 to the first is negative 1 times 2. Plus negative 1 squared is a positive 1 times 4. Plus negative 1 cubed is a negative 1 times 6. So we have 0 minus 2 plus 4 minus 6. Notice that the effect of the negative 1 to the n is to alternate the sign of the terms. So we have plus, positive, negative, positive, negative. Now, if I wanted to have the first term be negative, I could say, for example, negative 1 to the n minus 1, or negative 1 to the n plus 1, and then I could switch all the signs and make them the opposite of what they are. So that's how you do alternating terms with a sequence. And I haven't actually calculated the answer here. So I have minus 2 plus 4, which is positive 2, minus 6, which is negative 4. So negative 4 is the value of this summation notation. Now what if I want to go the other direction? What if I'm given this series of numbers, a sum that I want, and I want to express it using summation notation? First of all, you want to determine if it's arithmetic or geometric. It's pretty easy to do because you already know the rule needed to get all the terms in the sequence. You would just use the term rule. If it's not, then you have to look for a pattern. And if I gave you one of those, it would be one that has an obvious pattern. So the first one, we have 100 plus 85 plus 70 plus 55 plus 40 plus 25. This is an arithmetic, and and it has a value of negative 15 for d because we're going down 15 each time. So the way we would write it is make our summation notation. We start out with n equals 1, and let's number the terms 1, 2, 3, 4, 5, 6. So n equals 1 through 6. And then how do I find a term? I take the first term, 100, plus n minus 1 times negative 15. Now, sometimes it's nicer to clean this up a little bit. If we multiplied this out, we would have 100 minus 15n plus 15, or 115 minus 15n. So we could alternately say n equals 1 to 6 of 115 minus 15n. So either way is okay, although I think this is probably preferable because it's just a little neater and more concise looking. More concise. Okay, the second one, 500 plus 400 plus 320 plus 256. It turns out that this is a geometric, so we could say, we can figure this out. Remember that r is equal to 400 over 500, which is the same as 320 over 400, and 256 over 320. Now, if not all of those numbers are all the same, then it's not geometric, but in this case they are. R is equal to 4/5 or 0.8. You can use either one. So we know that then that a sub n is a sub 1, which is 500, times r, 0.8, to the n minus 1. So there's my rule. That's what goes inside the summation notation, because that's how I get a sub n. That's how I get each of the terms. So we would write our summation notation, n equals 1. Oh, we got some dots here. This means we go on forever. So what we have to put on the top is infinity. Okay, so we're getting an infinite number of terms here. 500 times 0.8 to the n minus 1. Now, can we find a sum for this? Well, actually we can, because r is equal to 0.8. So since r is equal to 0.8, we know that this infinite sum is a sub 1, 500, over 1 minus 0.8, which turns out to be, I think I've got this written down, 2,500. So we actually can find the infinite sum. Now, many times if you're given summation notation with an infinity sign up here, you may not be able to actually find all the terms and sums. You could just list some of them out and put a dot, dot, dot after them. But in this case, we actually can find the sum because it is a converging geometric series. Okay, last one. This one is neither arithmetic nor geometric. Not arithmetic or geometric. So we need to look for the pattern. And when we're looking for the pattern, what we want to do is number the terms. So n equals 1, 2, 3, 4, 5. And this is our term. Then as our a sub n is 1/3, negative 1/4, positive 1/5, negative 1/6, positive 1/7. What we want to do is look at the term and see how it corresponds to the term number. So 1 gives you 1/3, 2 gives you 1/4, 3 gives you 1/5, 4 gives you 1/6, 5 gives you 1/7. So notice that the denominator is 2 bigger than the term number. So in general, we can say 1 over n plus 2. However, we also have alternating signs. So let's start building this, our sequence here, our summation notation. So we make our symbol. We say n is equal to 1 equals 1 to 5. And then we say 1 over n plus 2, and that's the fraction part, but then we also have to alternate the signs. So then we have to say negative 1 to the what power? Well, if we say negative 1 to the n, then our first term is going to be negative, and we want our first term to be positive. So we're going to say negative 1 to the n plus 1. And that way, when we plug in 1 for n, we get negative 1 squared, which gives us positive 1. And so the first term is going to be positive. And then if we put in 2, we would get 1 over 2 plus 2, which is 1/4. And then we would negative 1 to the 2 plus 1. Negative 1 cubed is a negative 1. So we get negative 1/4, and so on. So that's how we could build this. Alternately, or we could start counting n from a different place. We could say, let's call this 3, 4, 5, 6, and 7. We could say n equals 3 to 7 of 1 over n times negative 1 to the n plus 1. Oh, do I need to do n plus 1? Yes, I do, because that's an odd number. So 3 plus 1 is 4. That gives me a positive number for my first term, which is what I want. So that's another way to write it. There's actually multiple ways to write it, depending where you want to start. The tricky part of using n equals 3 to 7 is that people sometimes mistakenly think there are 7 terms in this particular series of numbers, but there's only 5. It goes 3, 4, 5, 6, and 7. Sometimes people think there are only 4 because it goes from 3 to 7, but there are 5 because you have to count 3 and 7 both as term numbers. So be really careful when counting the number of terms in a sequence using summation notation.